Got some different, okay. So here's how we work through these. Again, what's the point of this chapter? So we're just trying to figure out the acceleration that was given in the last chapter. Let's go way back. So back to the basics. If I have a 25 kilogram force, we're going to build real kind of quick. If I had a 25 kilogram mass and a 50 Newton force, well, the acceleration would be pretty easy. It's just F equals ma. So 50 equals 25 a. Actually, Riley, if you have a calculator out, you can help me calculate today. That'd be pretty useful too. Kind of help us kind of go through. Some of this early on I'll be able to do, but I may need your calculations. So 25 equals 50a. Sorry about that little. Move this box. It's all I need you yet, but pretty soon. Maybe just be where you can see the screen. So a would be 2. Cool. So pretty easy. What if I were pulling this way with a 25 Newton force? Well, then you would say, well, there's 50 Newton force to the left, 25 Newton force to the right. My net would be 25 Newtons. So A would just be 1. Is that fair? It's just F equals ma. So where we started the other day was, what if I just had one force acting on the mass? It'd be acceleration of 2. If I had both forces acting, I would have to subtract. And then it would be 25 equals ma. What we're doing today is we're saying, hey, we don't know what this is. It's called friction. It's a force that opposes the motion. This is what this topic was about. And we have to go find it. We've actually got to calculate it now. So with this problem here is and this one's a little bit tricky. This is number 2. The reason it's tricky is because I have a 50 Newton force pulling 2 objects. They're not both in kilograms, so that's already tricky. I'd have to figure out the kilograms of this one. But also, because of this little guy here, this tells me that there's a force opposing, it's friction, and I have to go find it. So how do I find it? There's an equation we introduced the other day. Force friction is called mu times the normal force. Mu is given. It's the coefficient of friction. Normal is equal to all the weight. Here's where I'm going to need Riley. To find all the weight of this guy I can do, it's 30. But what's the weight of this one? Weight is the mass times 9.8. 1. Let's use 9.1 for this. Beautiful. Every now and again, I'll chime in for you. Thanks. So if the weight of this is 245.25, see, weight is mass times 9.81. If you're not sure, we toggle back and forth between mass and weight the same way we just use F equals ma. Newtons are kilograms times the acceleration, which in this case is 9.81. Or the mass is the newtons divided by 9.81. So for every object from now on, I'm going to need to know its weight and its mass. So sometimes, just to kind of mess with you early on, I'm going to give you, sometimes this is a 30 Newton box, or this is a 25 kilogram object. Turns out this weighs 30 Newtons. This weighs 245 Newtons. This one's mass is 25. This one's mass is 30 divided by 9.81. We'll need to know that later, but not quite yet. It's okay. Normal force. Normal force is equal to all the weight. Normal force is the support force from the ground that holds all my weight. Well, one box weighs 245. The other box weighs 30. I'll probably do this math. 275.25. So my normal force is 275.25, and the only reason I care about normal, generally we don't care about the normal force, right? Like, does it make me go? No, it's supporting my weight, but it's not you shoving me makes me go. The push or the pull makes me go, but the normal force is the ground. The only problem is I need that force from the ground to get friction. If I multiply 0.15 times 275, I can find friction. It's important to keep track of what we're trying to do. Like, what are we doing here? Here's what we're doing. We're trying to find the acceleration. I have a 50 Newton force acting on these two objects. I need to know their mass, but because that mu is there, because of this guy here, that tells me, hey, look, not all of my 50 is making it go. If you're dragging a wagon across the floor, not all of your force is making it go. That makes sense. If I'm pushing a box across the floor, not all of my force is making it go. This tells me that some of my force, 50, is actually going to be just to overcome friction. You ever pushed a heavy box, it's really hard to get it to go because of friction. So while I'm pulling with 50, this much is opposing. Where am I now? Now I'm ready to solve for the acceleration because the acceleration is F net equals ma. My net force is what's making it go. So what do I have? 50 to the left, 41.29 right. Those are not balanced. The ups and downs are balanced. The net force is 8.79. 1. 291, yeah, there it is. Newtons. And the mass that's going, now this is a little bit tricky. I know that it's 25, but the 30 newtons is not mass. So 30 newtons equals mass times 9.81, or the mass is 3. So there's a lot to this problem. They get easier as you work the problems. The ultimate goal is just to figure out what the acceleration is. What's the acceleration? It's the left and the right. It's what's pulling or pushing minus friction. The only thing we introduced in this worksheet is that we didn't know what friction was. We knew mu, but mu isn't a force. Mu is a little coefficient. It helps us solve for friction. Now that I do 8.71 divided by 28.06, 0.31. That's when you hope that's what's on the key. Otherwise, and it's going to go left. The 50 is going to win. But the point of this lesson, again, building, was trying to figure out what friction was. Again, the other day, we started off with so easy. If I just have a 50 Newton force point at 25 kilogram mass, its acceleration is 2. F equals ma. If I was opposing, I would have to subtract and say, well, only 25 newtons is making it go. Equals ma. This problem gets quite challenging because it says, hey, look, there's a force opposing. We don't know what it is yet. It's called friction. And to find it, we have to do mu, that little coefficient, times the normal force. And the normal force generally equals the weight. That's really hard. Illegible. Weight. Is that kind of okay? So that's how to solve those. Maybe if you're not sure, you can work back through those, or I can take other questions about them in a minute. I'm gonna go ahead and go on with today's piece, and then if we need to go back to those, we can. Okay, so that's how to do number 2 anyway. Number 1's easy. Okay. So today's piece is really about forces at angles. And friction's included. So what I like to do, the test is not next week, it's the week after, week test. We're only a couple days in. But I like to start hitting this heavy stuff, the hard stuff, as far out from the test as I can, so that we can spend a few days kind of letting it marinate some. Okay, I've got two examples. This is where I'll need my lovely assistant here to work through this. Let's increase that. This is similar to tonight's homework. Tonight's homework has 3 problems. I'm going to do 2 examples. The first example will help you with the first 2 problems. The second example will help you with the third problem. Okay, so what am I looking at here? I'm looking at a box being pulled by a force at an angle. This is like I'm dragging a wagon across the floor. I'm pulling at an angle. See, realistically, and this is what we have to start doing, realistically, when we're pulling things or pushing them, it's not always straight horizontal, right? If you're pushing a shopping cart, your arms are kind of down at an angle, or mowing the lawn. Your arms are kind of down at an angle. If you're dragging a wagon, your arms are up at an angle. So we're not always just left and right. And the same thing with projectile motion. The first week was just up and down. But how often is a ball going just up and down? It's when we throw it. So it's got that parabola. The same thing here. As I pull a box or push it or make it go, it's rare that the force is just left to right. So what if it's like this? The question will be simply, what is the acceleration for the test? Because I know that if I could find the acceleration and it starts at rest, I could find VF, VI0 and acceleration time. I could find out how far it goes. I could find out all those things. So this chapter is really just about solving for that acceleration that we kept getting last chapter. Okay. One other piece to this. Because it says with friction, mu is 0.2. So here's my box. What is this mu in case you missed the lesson on friction? Every surface has a different mu. That means it has different coefficients of friction. My rubber shoes on linoleum is like 0.6, pretty high friction, or like on wool carpet. But maybe ice skates, the metal on ice is like 0.04, really, really small. It just helps us calculate the amount of friction. We know from what I love about physics is that while this is forces, this is not projectile motion. This is forces and accelerations, it's not projectiles. But the same thinking applies. That force at an angle is going to be a problem. And you probably already know what you're going to have to do. Whenever we have something at an angle, the first thing we need to do is cosine and sine. Why? Because if I try to do F equals ma, let's think about F equals ma. I would love to do 180 equals 48. Acceleration would be 4.5. That's good math. Check that. 180 divided by 40. I would love to do 180 equals 48, but here's the deal. Not all of that 180 is making it go, right? I'm kind of pulling up on it some. But also, I got this friction piece up here. So because I have mu, and not all of it is making it go, what I need to do is, so I kind of understand my goal here. I need to figure out in red how much of my 180 is actually making it go. But then because of mu, I need to figure out how much is friction that's opposing. It's force friction, that's FF. Lots of forces. So how much is making it go? How much is opposing? Then I can do F equals ma. That's my goal. All right. First thing I do, just like projectile motion, is break it up. So this guy's going to be 180 cosine 25. That goes back to sine is opposite over hypotenuse. So sine 25 is opposite over hypotenuse. Cosine of 25 is adjacent over hypotenuse. Cosine is
163.
sine
76.7.
newtons. And just like last chapter, that 180 is kind of irrelevant to me now. It doesn't mean much. What's important to me is how much is making it go the 163 and how much is just kind of lifting up on itself. If you're pushing a shopping cart or a lawnmower, you might just flip this one as you push down some. The horizontal would still be good, but now you'd be pushing down on it some. I'll show you where that's important in just a minute. I'm kind of ready for the F net equals ma. This is making it go, except for the fact that I haven't done friction. So friction's a pain. Because friction means I've got to find the normal force. And the normal force is tricky. Let's talk about normal force. Normal force for the last couple days, and I know we moved quick. Normal force is equal to all the weight, generally. Let's talk about that. The weight of this is not 40 kilograms. Watch for test questions that say things like, what's the mass of a 40 kilogram object? 40. What's the weight of a 40 kilogram object? Not 40. Because weight is the newtons. It's the 40 times 9.8. So the weight, 9.81, is 392.4 newtons. Look for multiple choice questions that say things like, what's the weight of a 50 Newton object? 50 newtons. What's the mass of a 50 Newton object? 50 divided by 9.1. Just because it's so important to know the difference between mass and weight. What's the mass of a 40 kilogram object? 40. What's the weight of it? 392. Now, here's the challenge, the first challenge. I want so badly the normal force, the ground supporting this, to be 392. But there's a number I haven't taken into consideration yet. I know the 163 is making it go, friction's opposing, the 180 is gone, but what about this guy? If I'm lifting up a little bit on an object, does the ground have to hold all of its weight? No. On an opposite, if you were to come and push down on my shoulder, the ground better hold more. Right? Like if I lean on the table, the ground better push up with more than the table's weight. If I lift up on the table, the ground doesn't have to hold all of it. The normal force is a reaction force from the floor that usually holds the weight. If it's just like this, but if I start to lift up on it, then the normal doesn't have to hold all that. It's a missing up and down force that's going to make the ups equal the downs. So in this case, the normal is actually 392.4 minus 76.07. And hopefully that makes sense. The normal force is the support force from the ground, but see, I weigh 800 newtons. If Riley comes and lifts me up with 200 newtons, she's not going to pick me off the ground. I weigh 800 newtons. 200 is not going to get it done, but the ground only has to hold 600. If she pushes down on me with 200 newtons, then the ground better hold 1,000. Same idea. So the normal force now is going to fluctuate a little bit based on whether or not I'm lifting up or pushing down on the object. So my normal force is? Nailed it. The only reason I care about normal, the only reason, is because of friction. I can't find that missing force of friction without getting the normal. And today the normal gets a little bit tricky. The normal force is the support force upward from the ground That's usually equal to the weight as long as the forces are left and right. So in that friction worksheet, it's all left and right. The normal force will always be equal to all the weight, all the newtons. But now, if I'm lifting up a little bit or pushing down, I'm going to have to adjust the normal. My force friction is 0.2 times 316, 63.27. And everything we do is for a reason in physics. Everything is intentional. There's no number we just ignore. So the reason we found that was to find what's our end goal. We're trying to figure out how much of this is actually making it go. So follow me on the conversation. We started with 180 Newton force at 25 degrees, but only 163 was making it go. I want to do 163 equals ma. But because of mu, there's friction. So how much is that friction force? It's mu times the normal. And now I'm ready to do F equals ma. This is making it go. This is not. That's why I found that. So F net equals ma. 163.14 newtons is making it go to, woo, too many ones. 111. That's making it go to the right, minus 63.27 the left, equals ma. Your net force for this is that 100 newtons-ish, what, 99 point something? Beautiful. That's called your net force. The net force is not a real force. It doesn't really exist. It's the unbalanced piece. All my ups equal my downs. That's how I found normal. Go back and look. It's a good way. Like, hey, look, my box isn't flying off the floor. So does 316 and 76 equal 392? Yeah. That's how I found that. So my ups and downs cancel. My lefts and my rights don't cancel because this 163 rather to the right versus 63 left, those don't balance. So my net force is 0 up and down, but it's 163 minus 63 left to right. I will say for this chapter, much like projectile motion, you really just have to go back and look at the problems and just grind out with them and get them done. Going back and looking at your notes later is often like, I don't even know where we started. To me, almost overwhelming. So just try to remember things like the first thing we would do is break it up into cosine and sine. After that, I really just want to do F equals ma with the part that's making it go. But because I didn't know friction, I needed the normal force to find it. And then I can do F equals ma, and my A ends up being 99.87 divided by 40, 2.5. This is very much like problem 1 and problem 2 in the homework for tonight. Cool. One more? Yeah. Yeah. Oh, good question. So, and that's not M. Let's be a little bit careful. Some folks are saying, well, it's kind of like a cursive M. M is really mass. Mu is a little, it's a lowercase. Yeah, it's a Greek letter. Mu alpha theta, is that the math group? Phi mu. Might go Greek, I don't know. But mu is a lowercase mu, capital mu is M, I think. Just a big M. That might be mega. I don't know. Good. It's Greek. Yeah, the little squiggly U. Okay, let's do one ramp. And this is going to be an easier version of the ramp. If you're not here tomorrow, we're just going to be kind of adding things to our ramp. So this is the basis of our ramp problems. this is kind of the beginning of the end of the road for this chapter. Beginning of the end. Mu is given, it's the coefficient of friction. That's generally tested in a lab by somebody putting metal on ice to see what the coefficient is. Or again, rubber soles on linoleum, or rubber soles on carpet. It's the coefficient between any two surfaces. That part will be given. What that tells me is I've got to take into consideration friction. Okay, so this problem is a little bit funky. In game, and it's going to get messy. Boy, these problems look so easy. I mean, it looks so simple, right? They get ugly. I just want to know what the acceleration is as it goes down the ramp. I've got a box on a ramp, tip it, it's going to slide. Beautiful. Okay. So what's happening here, if you can imagine a box on the ground, it has weight, and all of that weight is supported by the ground. So it's not going anywhere. Push it left or right, sure. But if it has weight and all the weight is supported by the ground, it's just not going anywhere. If I tip it all the way up, the ground's not holding any of the weight. It falls. And it accelerates at 9.81, as you would expect. It's in free fall. So somewhere between zero acceleration and 9.81 is what we're going to find. As we tip it up, the force of gravity is always down. So let's find that number first. That's going to be kind of what's driving this thing. Now, what is the weight of a 50 kilogram object? Not 50. What's the mass of a 50 kilogram object? 50. The weight is mass times 9.81. So 50 times 9.81. Calculators. Nailed it. Okay. So 490.5. Now here's what's tricky. Not all of that is making it accelerate, because if it was, it'd be 9.81. But it's not accelerating at 9.81, it's not in free fall. So what I've got to do now, and this is going to be a little bit funky, I want to kind of mess with this a little bit. What if I turned it like this? Don't necessarily do this other than if you have paper, you could do it. But if I turn it like this, what it looks like to me is that part of gravity is just straight into the ground, like it normally is. Like get normal, yep. But part of it is making it go this way. Fair? It's almost like gravity is what's at an angle. So when I rotate this back, that's exactly what's happening. Is that some of the force of gravity is actually into the ramp, but some of it is making it go down the ramp. We call this the force sliding force. And this is force normal. That's the normal piece. So it makes sense that the normal is not 490.5 because the ground's not holding all of it. It's sliding. If the ground was holding all of it, it wouldn't be going anywhere. So how do I find those two pieces? Your trig stuff. If that's 40, then this is 90, that's 50, but really this long story ends up being 40. So long story right here in green, this angle in green is what we want to focus on. And that angle is 40. So if your ramp angle is 40, that angle, this angle up here ends up being 40 as well. And why that's really nice, this is a little bit confusing though. Why it's really nice is I can use cosine and sine to find these pieces. What's a little bit confusing is that the blue one is actually your hypotenuse. We're not used to straight up and down being the hypotenuse. But in this case, that is your hypotenuse. So the normal is going to be 490.5 times the cosine of 40. And sliding is going to be 490.5 times the sine of 40. So this piece here is the opposite. Turns out that gravity is actually your hypotenuse. It's a little bit funky the way it looks. Now, back to this. This is clearly, you'd be like, yeah, the blue one's the hypotenuse. But for some reason, when it's on the ramp, it doesn't really, my eye kind of says, no, maybe not. So the normal piece is cosine 40, 490.5 cosine 40.
75.74.
Almost done. This is our last example today. The sine piece,
15.21.
so what am I trying to do here? What am I trying to do? I'm trying to figure out the acceleration of the box down the ramp. But all I've got is the 490.5 of gravity. But because that's straight down, not all of that is actually making it go down the ramp. Some of it's kind of into the ramp. So what did I just find? I found that this is what's actually making it go down the ramp for F equals ma. If I didn't have friction, that'd be it. That's making it go. That piece. But that mu tells me I've got one other little problem. I've got 315.29 making it go. We call that force sliding. Is making it go. But the mu up there says, yeah, but you've got friction. But how do we find friction? Friction is just mu times the normal. And this one's kind of nice. There's no other forces like pushing or pulling or pushing it into the ramp, lifting it off the ramp. The normal is this piece. So I can zoom back out in a minute. What have we done? We took 490.5 and broke it up into how much is actually going down the ramp, 315, how much is in the ramp, 375. Why do I care about the 375? That's going to give me friction, so I can subtract from 315, do F equals ma, and I'm done. Friction is mu times the normal, which is 375.74, which is 112.72, and that's when you really hope that that's smaller than 315, but it is. If the friction is 112.7, not 117. Now I'm done. I'm ready to be done. What's making it go down the ramp? This piece of gravity, the 315. What's opposing that? The friction, which is the 112. So acceleration always comes from F net equals ma. And in this case, the net force is 315.29 minus 112.72. The thing's in kilograms. So this is really what I'm trying to accomplish. I just want to do F equals ma. But the only force I knew originally was 490. 490 is not making it go. How much is making it go? 315. How much is opposing? 112. The net force is 202.57. That's making the 50 accelerate. I certainly hope I get less than 9.81 because 9.81 means I'm in free fall. Can't really be bigger than 9.81 here because there's no other forces acting other than gravity. But you can see the acceleration is going to be around 4.1. It is a vector. You could just say down the ramp. Working backwards, my end game is just this. If you want acceleration, you've got to just solve F equals ma. Did you have the mass? Yes, you started with it. The problem is what force is making it accelerate? What's the net force? And if you look back to the problem, the only force we had was gravity. But that 490.5 wasn't making it go. We have what's called force sliding, the sine piece, using 40, and the normal piece, which is cosine. Sliding is making it go. And then I just subtract friction, but friction I have to use the normal force. This is nearly identical to number 3 on your homework. So the first example will help you with 1 and 2. This will help you with number 3. The only thing we're going to add in the next couple days are what if I had this, but also a force, like put 1 and 2 together. That's as tough as it gets. Pretty challenging problem. Where if I got this going on the ramp and it's all angles and kind of funky. That's in a sense the end of the chapter. We're only 3 days in, but what we're going to do now is word problems. Okay. That's the end of the lesson. You got a few homework problems. Now I can take questions. Check it.